All right, welcome everyone. I kind of just gave a little bit of the preamble, but today we'll be looking at scaling up graph neural networks. We're following along with this Stanford course. I think this is a pretty interesting topic because a lot of these graphs that we're interacting with are very large. If you want to do something useful, it probably touches on a graph that can have many, many nodes, many, many edges. And so this will be talking about the tricks to make that fast and make that efficient and even operate on a graph that's web scale. So skipping over the logistics part. So there's all kinds of stuff that you can do with graphs, and looking at all of these systems that typically have them, you look at stuff like Amazon and their product recommendation, and YouTube and their video recommendation, and Pinterest trying to recommend various different things to you. There are tons of users, and there's also tons and tons of products or videos or any other number of things that they might want to show you. And so these can be on scales that are millions, billions, maybe even beyond. And so you have to think about how do we manage these? So there's all kinds of tasks that you can do here in terms of link prediction or node classification, and a bunch of other stuff as well. But the big problem is we have so many nodes, so many edges. It's easy when we have a small little toy task where we just have a few people and a few products and stuff like that, but it becomes very difficult when there's so many different nodes and edges that we need to kind of repose things. So that was true on recommendations. It's true on social networks. So Facebook might try to tell you who are the people you might know, what are the posts you might be interested in looking at. And so there's all kinds of stuff that you can do there. There's also, so like one of the examples is academic graphs. So you can have this mixed graph that has all different kinds of data. So you can have authors and papers and institutions and this heterogeneous mix. So this can be very large as well. There's many people who write papers, there's many different universities, and they all have different relationships to each other. And so that kind of big, massive, interconnected graph, you have to deal with it in some way. And there's a whole bunch of different tasks that you might want to do beyond that, but you want some method that's able to scale up to them and also do all of the different kind of tasks that you might be interested in. Another one is knowledge graphs. So you have something like Wikidata or Freebase or something like that, and you have a whole bunch of things that have kind of all of their mapped relationships. And so you have another set of tasks that you might be interested to do on knowledge graphs. We haven't done much with knowledge graphs yet, so I won't go into too much detail. So I've already mentioned this a few times, but you can have millions or billions of edges. You can have millions or billions of nodes. And so we need to figure out how exactly to scale that up efficiently and make it even feasible to operate on something of such large scale. So the big problem that we need to overcome is in regular machine learning applications, not on graphs. It's fairly easy to just say, well, we have 1 billion points, let's just sample 1 million of them, and then we can operate on that subset as we train, or we can train on subsets over and over again. So you have 1 billion points, but then you sample 64 of them and you train on that batch, then you do it over and over again. This works really well in general machine learning tasks where you can do that sampling and do many batches and just eventually kind of average over those subgroups. But there's various problems in the context of graph machine learning that makes it infeasible. So the major one is you look at a graph like this and you say, I have 1 million nodes, I have 5 million edges. If you just sample certain nodes, so you go in and you say, I want 64 nodes, the problem with that is you're disconnecting from the rest of the graph. Then you're not saying, okay, here's Ted and all of his relationships to everything else. You have Ted, and then you have some person in Serbia that Ted doesn't know, and the links don't matter. There's no connection there. You need to be able to look at the things that are interconnected to have anything useful in terms of a graph neural network. So this random sampling of nodes doesn't work in the context of graph neural networks. So we need to look at some other strategies in terms of how do you build a graph that keeps that interconnectivity. So one of the approaches, kind of the naive approach, is to go and just say, we'll just load everything. So you load the entire graph, and then you have the entire thing in memory, and then you compute your embeddings, and then you do all of the rest of the graph neural network process. This would be great if we could do it, but it would be extremely slow to load in potentially billions of nodes and edges. But even worse than that, we probably can't even do it realistically, because you have to calculate the embeddings for the entire graph potentially, and we just don't have the memory to even do that in most cases, especially if you want to operate on GPUs. That would significantly speed up all of these calculations. The memory there is even more limited. So full batch would be too slow. We wouldn't be able to fit it in memory. The insane thing about the full batch is you have to not only have the entire graph in memory, you have to have multiple hops of that graph. So you say, I have the graph, and then now I want to calculate the messages of all of those connections. Then you have to have the initial graph and all of the relationships of that graph. And then if you want to do another hop, then you have to do the relationships of the relationships. And then now you have multiple copies of this graph. And the memory has just exploded, and it's just completely infeasible. And then you have to go and do the full backwards pass through all of that stuff. So it's just an insane amount of memory. You're not even close to having the capacity to doing that, even on a somewhat small graph. So overcoming that is the point of this whole chapter, basically, is how do we overcome this limitation we have, and how do we operate on something that's so big? And so looking at even large CPU instances, you might have a terabyte or 10 terabytes of working space, but it would be extremely slow. So you wouldn't be able to calculate all of the embeddings and all of the message passing and all of that stuff. Even if you could fit it in memory, it would be too slow to really be feasible. And then you look at GPUs, and it's just your order of magnitudes off from even being able to address something like this. So the various techniques that we'll be looking at is neighbor sampling, cluster GCN, and those are mainly focused on how do we take subgraphs that are useful and then compute just on the subgraphs. And then the other approach that we'll look at is simplified GCN, which will basically kind of simplify the GNN architecture to the point that you don't have to do all of this complicated multi-hop calculation. So the first one we'll look at is neighbor sampling. So this came from the GraphSage paper. We've talked about that in some previous chapters. This is another one of the useful tricks that came from that paper. So just kind of remembering how these graphs work, you pick some target node, and then you have to look at all of the interactions around them, so all of the connections. So for example, let's start with node 0, and then what's connected to node 0? It's 1, 2, 3. So that's how this works. We have node 0 that retrieves information or aggregates information from nodes 1, 2, and 3. And then if we want an even deeper representation, we can go a second hop. So we have 1, and that aggregates information from 0, 4, 5, 6. So one thing to note is that we have this 0 here again. That's saying that 0 is actually going to receive information from 0, and that information is going to propagate all the way through. So this is this would be the features of that information. So for example, if this was me and you had information on my zip code and my income and various other things, then you might be able to predict house price or something like that. So this would be different features than is ending up here. This is kind of an aggregation of all of the interconnections and all of that stuff. So the big takeaway from this neighborhood sampling is eventually we will gotta review the slides. So the trick that we can do here is, before we were looking at loading the entire graph in all at once, but that's just too much. So what you can do is you can select individual nodes and you say, okay, pick the Ryan node and then just look 2 hops away and load in that specific graph. So you would start with me, and then you say, what is Ryan connected to? He's connected to this, this, and this, and then that's connected to this, this, and this. And if you stopped at 2 hops, then you would say, okay, just load in the information relevant to those 2 hops around Ryan. And so that greatly bounds the computation, because it means only load in the stuff that is relevant for that specific batch. So you can go and you can load in 64 nodes and all of their connections, and then you get the full interactions and depth of that without needing to load in everything. You're only loading the stuff relevant to that specific target node or set of target nodes. And so this makes it much more feasible. This makes it so you can greatly reduce the computation. And one of the extra tricks that you can throw in here is layer-wise embedding. So with this, one of the problems that we run into is there's a lot of redundant calculation. So for example, if you had a simple graph like this, you have A, B, C, D, and let's say that A is our target node for now. We would have to calculate the messages for B, C, D. And so you do some embedding on these features, and then you pass it to A. And then let's say we wanted to compute something for D, or we're just doing the second hop of A. The problem here is then we have to calculate A, B, C. And if you look at the overlap there, we already calculated B, C, D, and now we're calculating A, B, C. That B, C portion is redundant. We've already calculated that before. So the trick that you can do there is you can basically look at the entire graph that you need to calculate for, and then you just calculate all of the features, and then you do the message passing after, rather than doing them one at a time and then doing a whole bunch of redundant calculations. So you say, here's all of the nodes that are relevant, calculate all of their embeddings, and then do the passing. And that makes it so you just compute the embeddings once, and then you do the passing, rather than doing that over and over for each node and potentially redoing a bunch of calculation every single time. So this is one of the tricks that helps make it more feasible, is just reducing all of the redundant calculation. So that's one of the problems, is all of the redundant calculation. But then the second one is you can end up with extremely large graphs, even if you're only doing 2 or 3 or 4 hops. So if you say this node is very connected to a bunch of other nodes, for example, or just it's connected to another node that's very connected to other nodes, you can end up with something that has a massive graph. So for example, imagine you have something where it's like one node is America, and then you have hundreds of millions of people that are connected to America. then you have this problem where all of a sudden the graph just got completely huge. So one of the tricks is you can limit this in some way. So instead of taking all connections, you can sample the connections. So we need to figure out exactly how to do that. So one of them is we can use this variable h, and that will determine how many hops we actually we actually are not hops, the number of connections that we actually consider. So we only look at h neighbors potentially. So we start at node 0, and then we look at this and we see that it has 3 connections, but we'll only look at 2 of them. We'll just discard this one. This will just make it much more feasible to actually manage something like this. And it puts some guardrails on the case where you have something like America, and then it has all of the people inside of it, and then you have way too many connections, and it just explodes the graph. So setting some value of h and just sampling the number of connections makes it so you're protected in that regard. So for example, we pruned the node here, and in turn that pruned all of this stuff, and then the next step we got 0 and 8, but we dropped 7. So this defining h and how many neighbors you sample is very useful as a guardrail against that, to make sure that the graph stays a feasible size. So this is what the pruned graph might look like. You save a whole bunch of computation on that, but then the trade-off is you're losing information. So we no longer know anything about node 1. But the theory is you do this enough times and you've sampled enough nodes that eventually next time you might pass and get 1 on the next batch. So you do learn something about 1 later. You just might not get it on every single pass. Eventually you kind of average that in. So then the trade-off there is you have higher variance. So the problem is if you drop 1 and that was important information, and then next time you drop node 3, you're going to get a lot of variation in between each time. So the graph might look very different. You might get different results depending on your sampling, but we need to do this in some way. So you have to kind of take that hit on larger variance. You're not getting every single node every single time, but this makes it much more feasible. So one of the things to note on the scaling here is for every k hop. So k is the number of, it's sort of the depth. So it's how many relationships deep do you go. So if it started with me, it would be Ryan's connections, and then those connections, and then connections, and then at that point you've gone very deep. So that's what k is. So if you had that set to 3, that would be connections. And this h gives us a better bound, but it still makes it so you can end up with exploding graphs. So if you set h something like 5, then you're doing 5 to the 3rd, for example, for 3 hops. So that's many multiples of that calculation. It can be possible, but you have to be aware that changing this h and changing this k can have massive impacts on the performance of your network, just in terms of compute time, because changing that slightly can be many multiples of complexity increase. So one of the things we were looking at is on the previous slide, we just sample away some of the nodes. So we could do random sampling, but we probably don't want to. There's probably a better strategy than just saying, okay, this time I'm going to drop 1 and this time I'm going to drop 2, etc. There's probably smarter things we can do. So random sampling, that's one option. That's kind of just the baseline. And then people have said, well, wait, we can do better than that. So in previous chapters, we talked about random walks, And so random walks, basically you start at a random node and then you just kind of wander around and you say, okay, this time I'm going to go to that node and then that node and then that node. And you do a whole bunch of random walks and you basically see where on the graph you touch. And so the points that you touch more often end up becoming more important because that means that they're highly connective and they have a whole bunch of inbound edges. And so doing random walks on this, we can figure out what are highly connected important nodes. And so we can use the score that we derive from random walks in order to inform our sampling. So that will point us in the direction of the nodes that are more useful. So with that random walk, then we point at the stuff that's more useful and we do it better than just random sampling. We can actually get a better result with that by focusing on the nodes that are actually important rather than just completely randomly dropping certain things.
Ryan, super quick question. I think you would only need to calculate the relative importance of nodes once, right? And then you can just catch that for the whole rest of the training process.
Yeah. Okay. Because assuming your graph isn't changing, you do it on some fixed graph and then you calculate all of that and then you know what's going on. But you might have to calculate again in the future if things change. Right. Just during
but for one training session, it's just a fixed one single fixed pre-compute.
You only do that once and random walks are quick to compute. So it's not a huge cost, but you're not doing that live during the process. You have that pre-computed, and then that that gives you a sort of weighted random sampling rather than just completely even random sampling. There's a question about why random sampling is more efficient. I don't know that that's necessarily the case.
I think what you were saying, Ryan, is that random walk sampling gets you a more accurate importance weighted sample than a uniform random sample. They're still they're both random samples, but one's uniform, the other is weighted based on the random walk frequencies, so that if you're doing some like Twitter thing and some famous person has a million followers, there could be Ted, who's a follower and is like totally unimportant, but then there could be really influential people, in the music business, really influential people in Hollywood who are followers. And so those people might carry a lot more weight. So if you're sampling some of them at a higher frequency than just random Joe Blow, then you might converge to a more accurate representation of the neighbors. Is that the gist?
So my trying to create an example on the fly, imagine that you have some website, for example, and it has a whole bunch of links, and it goes to a whole bunch of random sites, but then it also links out to Amazon and Facebook and various other things. It's probably more informative to point at Amazon and Facebook and whatever big sites rather than some other site that has no other interconnections, because you have more similarity with other things. So getting that inbound information that it has links from Amazon tells you more about the stuff that it's related to than some random site that has no other connections. If it's a dead end, then it probably doesn't tell you a whole lot. So one is uniform, one is informed. I would say that's a reasonable way to look at it. So the random walk points more at the relevant nodes, the more important ones. So looking at the neighbor sampling, Couldn't you sample according to something like degree? That wouldn't be uniform, but then random walks also gives you connectivity. I'm trying to think how, I'm sure you could do something like that. I think random walks are preferred because it gives you a deeper look at the actual interactions deeper into the graph. So you might not be directly connected to Amazon or Facebook, but you're one hop away and a lot of your links end up getting there. But if you were just looking at the in degrees or out degrees or something like that, you might not be able to capture that potentially. Um, I'm sure that's a viable strategy, though. I think people probably tend towards random walks. Those are random walks are interesting because they give you a lot of information. There's something very simple to compute. So I think that's the big benefit of random walks. So reviewing neighbor sampling, the big takeaway is we take the subgraph of just the stuff that is relevant to a specific target node. So we go and we say, let's pull 64 points, but then on top of that, let's look at all of their K hops connections. So then on top of that, we also do that pruning or subsampling. So for example, we set H, which told us only look at 5 connections, for example. And then we go and we compute the embeddings for that entire graph. And then we do all of the message passing and all of that stuff. And so just doing that kind of order of sampling, building the subgraph, and then computing the embeddings only once and not doing redundant calculations, it can make us many orders of magnitude more efficient. So we'll see in the next set of slides that it's still not perfect, but it is something that makes it much more manageable. And we can choose various different parameters of H and K, et cetera, that make it so we can handle a graph of pretty much any size. So the next one, we're choosing between the different methods largely depend on context of data and problem you're trying to solve, or are random walks a general method of exploring? I'm sure in all cases you probably can do some tuning for whatever your problem is. But I think in general, random walks should give you a well-informed answer. I don't see much reason why you would expect random sampling to do better than random walks. But I think the other parameters like H and K, those will probably be dependent on the structure of your graph and what you're trying to do and everything. But I think that's true of every machine learning problem, is there's parameters that you can tune depending on your problem. Some of them might be relevant, some of them might not. It just depends on what you're trying to do and what your graph looks like. So what if we do message passing once just to cluster some communities based on similarity and do random walks to those communities formed and do the required test? So that's kind of what we'll look at in a second, is we'll do something sort of similar to that. So that's the whole concept of this clustered GCN, is looking at the clusters of communities and then working on them. So we'll talk about that a bit more in a second. So this is similar to what we talked about before. The computation graph is very redundant. So if we're computing stuff for A and we're computing stuff for B, and then we look at this, we're connected to both C and D on here, and then B is only connected to E, A isn't connected to E. So if we look at this, C, D is redundant in both sides. So CD is redundant, E is unique, but what we want to do is we only calculate CD once and then we share it across both of them rather than doing the same calculation both times. So that's, I already mentioned this technique, but here's another visual to match along with that. So this is kind of the layer-wise embedding that I was talking about. Is basically you want to compute all of the messages. So you take all of the features, you multiply that by whatever weight matrix, and that gives you all of your embeddings, and then you do that for the entire graph that you have, all of the nodes, and then you just do your message passing, and then you can do that again. And so only doing this once makes it much more efficient because you're only computing one big matrix multiply, basically. You can just say, here's all the nodes, here's the weight matrix, apply them together, and then you do the aggregation, and you can do that in one big step, rather than doing it per node, looking through the depth and all of that stuff. And then we can do some kind of conditional random walk based where decision is done for the walk based on more similarity to our target node. I think that's similar in nature to what this cluster GCN will do. So we'll just talk about that technique, and then maybe we can revisit that idea in a second. So this layer-wise embedding, we've already talked about this a couple times, so I won't go into too much detail. But sometimes it's not possible to fit the entire thing into GPU memory. But we will typically get around that by doing some form of subsampling or pruning or partitioning that will make it possible for us to handle that. So one of the problems is we start with the big graph, and then we can sample that in some ways, but we want to sample it in a useful way. So this is kind of different from the other one where we were picking nodes and then we were building the graph around that. Instead, we can do a sort of subsampling, and then it helps us more efficiently do this layer-wise embedding process. So one of the things we really want to focus on is capturing the edges. So like I was mentioning before, if you pick me or if you pick Ted and then you sample another point and it's someone in Russia or something like that, we probably won't have connections to them and it's not very important. So you want to maintain those edges. That's very important, is capturing the people that they're connected to. And so looking at a few different options. So let's say that we have this original graph, it's a fairly small one, but we have two different ways that we can sample them. This is just randomly choosing. If we had an option between this sampling on the left and this sampling on the right, we would prefer the one on the left because this one shows all of the local interconnections, and this sampling on the right isn't very useful because it's all of these disconnected points. So if we look at this node, for example, we only have this one connection. So that's not very useful. That's not as useful as seeing here's all of this stuff that this top left node is connected to. So just summary, left graph good, right graph bad. So if we can, we want to sample like this as much as we can, and we want to avoid sampling like the right when possible. So this is kind of going off that point we were discussing more, is you want to pull in local communities. So we can do something like clustering, and that will bring in and say this whole subgraph, these are all related. There's a lot of connections here. So for example, you might say like this is the computer science publishing community, this is art, this is history, for example. And there are connections between these, but in general, these kind of nucleus are all related to each other and might be separate from these. There's probably some connections, but it's not nearly as much as the stuff inside of that cluster. So what we can do is we can partition the graph in various different ways. So for example, in the previous weeks, Ted talked about some clustering algorithms and community detection and stuff like that. And so what you can do is you can find the communities, and then you sample in entire communities. So rather than just saying, I'm going to pick a point and then build around that, you can say, I'm going to sample a whole community and then I'm going to operate on that community. And because it's a close set of interactions, you can represent the entire subgraph there for that specific community. So then what you can do is you can during training, sample in one of these specifically and operate on it slightly more intensively. And then you can train on the whole computer science community, on the whole art community, on the whole history community independently. And you can be slightly more efficient there if you're operating on one of them at a time. So like Ted mentioned in previous chapter, you can do something like Louvain, and that will tell you the communities within a graph. And then you can say, here's group 1, here's group 2, here's group 3, and then we can operate on those on their own. So this helps us be more efficient, basically saying grab all of these nodes from a certain community and then build that subgraph and then operate on that subgraph on its own. But then so then we can do the layer-wise updating like I was mentioning. But then the big problem with this is if you're operating only on a specific community, then you don't have the connections with the other communities. So for example, if we just said only operate on the computer science community, we have all of the information of the computer science community, but then we don't have the connections to art or history, for example, and that could be crucial. You don't want to have that isolated group and then no information about anything outside of it. That's just not realistic. That's putting a lot of faith on your clustering or community detection algorithm, and it's probably not giving you the information of the whole graph. So for example, we're missing these big inbound, outbound connections to other branches. So we have to figure out what do we do to address that. So this is what it might look like. So we have a big graph with all of the nodes, and then we've detected a specific community, and then we're operating just on this specific subgraph that we detected. So one of the problems with this is that we are going to operate on just that small shard of the graph, and it's going to be all of these things that are highly correlated. So if we just operate on the computer science subgraph, we might be able to learn something about that, but then next time when we swap to the history or art subgraph, all of a sudden things are going to look very different. And this is going to cause instability in our network where we're saying one batch is all of this kind and another batch is all of another kind and then another batch is all of another kind. That makes it so that an individual batch is not very representative of the entire graph. So you're pulling your network in a bunch of different directions every single batch. So it is possible to converge in this method, but it's very hard and it can slow things down quite a bit. So this isn't really optimal. Even if you do the clustering, then you can end up with problems where you can't converge well because of the bias in your batches. So one of the tricks to overcome this is you can aggregate multiple node groups. So you do that community detection, you find a whole bunch of groups, and you in this case you tend to make them even smaller. So if it was CS, you might go even smaller, a sub piece inside of computer science, because you want these to be relatively small. And then what you do is you will then, when you do a batch of training, you don't just pull in an individual group, you will pull in multiple groups, and then you'll build the whole graph for those groups together. So for example, we go over here and let's say we have the whole big graph, this is everything, and then we've detected various different groups inside of it, and then we do sampling. Instead of just sampling this, we sample both of them, and then we also do the interconnection between them. So now we're operating on something that is combined, that might be some subgraph of computer science, some subgraph of art, and then we have their entire subgraphs and then also the connections between them. And so we have the relationships between the groups, and we also have the groups themselves. And so this can give us, it's not necessarily the best of everything, but it gives us more information about things, and it makes it so our batches aren't completely biased towards one individual subgroup, because when we're operating on it, we actually see the combination of multiple of them. So then we can have the combination between this group and this group and this group and that group. And so we have a more complete look at the graph, and our batch won't be just one specific subgroup every single time. So that's kind of the major idea behind the cluster GCN, is you do those clusters, you grab groups of clusters, and then you build a whole subgraph around those nodes that you selected. And then that gives you this sort of group of subgraphs that can build something useful and you can train against. Is it kind of hypernode community cluster? I don't know exactly what you mean by hypernode necessarily. I'm not sure. Sure. I don't, Ted, do they have unmute?
Yeah, so my voice is audible.
Yeah.
Yeah, so first of all, really excited to be in this community right here. What I was actually thinking was, suppose making the community detections, we are actually clustering with some kind of community. And suppose we just do for one more hop where we treat each community as a hyper node, like pooling all those community features as a one complete node, and then treat those sets of community as a different kind of graph, such that the resultant what we will get is actually like a more distant communities are actually getting close enough to each other, such that we can actually cover the whole large billion nodes graphs as a one, and such that the when our resulting graph would come, it would be a more efficient in order to do the other downstream task. So
Yeah.
I was just saying in that perspective.
Yeah. So if I understand what you're saying, so right now what we would be doing is we have this subgraph and then we have this subgraph.
Yeah.
And we're kind of just picking them and pairing them up randomly, but we might want to have something more informed where we say, okay, computer science isn't that related to art. We want to connect it to something that's maybe engineering or something like that. That would be more relevant. And so you could do that hypernode technique to find the other subgraphs that are more connected.
So it's something like similar, like suppose we have an Indian machine learning group community and a Serbian machine learning group community. At the end of the day, both are actually machine learning communities, right? But if we see spatially, they could be wide, means different from each other, or it could be very distant to each other, like initially. But if we could treat in this way, like as a hypernode, and then treating those sets of communities as single nodes, and then making a more as a recursive cluster formation, then we can actually group Serbian machine learning and other different distant machine learning groups as a one complete machine learning group. This would this
Mhm.
might work as a more efficient or some bit of, I don't know. I'm
Yeah.
just like saying, got some thoughts. Yeah.
Yeah. Yeah. I
So
mean,
Ryan,
that's, go ahead.
if I could jump in, I think anytime you do hypernodes, it's fine if you're looking for more global structure, but you're probably going to lose local structure. So if you were just
Yeah.
trying to like see like these large trends in like popularity of machine learning between India and Serbia or something like that, then or whatever, you know, like idea flow from country to country, then yes. But if ultimately what you wanted was some very local phenomenon like recommending friends to individual people, then I think the super
Hmm.
node is probably going to lose too much local structure.
Yeah. Yeah. That's also it's.
Yeah. I mean, I can see that idea being useful though. That's similar to like before on the other sides, we were looking at random sampling versus random walk sampling. That it's kind of similar idea where it's like, let's just pull in subgraphs that are actually more related. But I also wonder on that sort of macro scale, if you do probably want to do um, more random sampling so you don't end up with subgraphs that are just correlated again and you're just building up a larger one from your two subgraphs. But yeah, I haven't seen that technique used, but I could see it being useful. What's the name of the topic? Is it hypernode theory? Um, I don't know the formal name of it, but I would bet that's a reasonable thing to Google to try to find it. Basically, the the idea is to take this subgraph and then kind of simplify it to a single point and then say find what that single point is related to. So find the other subgraphs that are, so find the connected communities basically. um, so that's how I would describe it. I don't know the formal term for it.
Yeah, I don't either. My intuition is if you have a problem where you were wanting to run a graph neural network in the first place, because there are other, you know, graph algorithms that don't involve GNNs. And if those work, they're probably cheaper and you can use those. If you want to use a GNN, then I don't know that this coarsening or hypernode is going to be a very common choice. Um, but I could see that if you successfully use some of these techniques to speed things up and you're able to create all the node embeddings, node encodings, then there might be ways in which you do cluster and maybe you average features across clusters in order to you know, do analysis and make inferences about these giant graphs, right? But my intuition is that's going to be a little bit scary when you're trying to actually train the GNN and actually build these node embeddings. I think because remember, I mean, GNN just starts with randomly initialized weights, so you really need it to train well. Um, and so I think anyway, that's my 2 cents. But again, you know, we're all learning this together, so I do not claim to be an expert in graph data science.
Um, so yeah, that's the general idea of the cluster GCN. Is do the um, we do the clustering, we grab from those clusters, and then we pull in multiple of those clusters, build a whole graph around that, and then we can train on that grouping of clusters. And so looking at the complexity of this, we can compare the neighbor sampling, which if we remember, that was the one where you pick a point and then you build the graph around that point, is different than the technique we were just discussing. If we look at the neighbor sampling, We have the number of nodes that we're looking at, and then we have the H, which was that parameter where it's saying how many neighbors we're going to look at, and then K is the number of hops that we're going to do. So we can see that we have this exponential that can cause many problems. So if we are connected to, if we're saying we set H to 5 or something like that, which isn't even that big of an H necessarily, and then we say we're doing 3 hops, for example, we can set K to 3, we're already doing 5 to the 3rd times as many computations. So that can end up being quite large potentially. And then we compare that to clustered GCN. What ends up happening is its total complexity ends up being K, which is the number of hops that we do, and then M is the number of nodes, and then D average is the average number or the average degree of connection. So if we look at this has removed that H to the K that can end up being a problem for us, depending on our H and depending on our K. It can be manageable, but this kind of prevents that from ever being a problem. Really, you can, like, if you set K high, it's always going to end up being a problem, but in general it protects against kind of runaway complexity like that. So here's complexity for neighbor sampling, here's complexity for cluster GCN. And so they kind of lay out this example scenario. Let's say that you set H to be half of the number of average connections. So your average node has 10 connections, for example, and so you do divided by 2 for you set H to 5. If you do the math on these, you end up finding that cluster GCN is way less than the neighbor sampling if you plug all of those numbers in. So M is constant, so we can basically take that out of the equation. And then we have H times K instead of H to the K. So you end up with something that's much more feasible. So one of the things they mentioned in the Stanford lectures, though, was it seems like people still tend towards neighbor sampling. I think that probably depends on the connectivity of your graph and size and everything like that. I think that they didn't really mention the actual performance, because I'm sure that these lead to differently accurate models. You're not going to get the same training result out of neighbor sampling and cluster GCN. So it would be interesting to see a comparison between those two in terms of performance versus just throughput, how much training you can do on top of them. So just summarizing again, we do the partitioning of the graph, we do that clustering, and then we build the multiple subgraphs together. We take all of those nodes, and we build the graph with the various communities that we sampled in, and then we do that layer-wise node embedding on that graph. And then we discussed cluster GCN is more efficient than neighbor sampling. But one of the downfalls of that cluster GCN is we can potentially be missing those cross community edges. So if you have the CS community and you only work on that, then you're missing the connection to art, history, etc. And we can get around that by sampling in the different communities as well. But you're still going to be more biased than the neighbor sampling, where you're just building the whole graph and all of the interactions with them. So pros and cons to both. So this final section, I don't think I'm going to go into too much detail into it. I vaguely understand the idea, but I don't know that I can do it total justice. So the big takeaway that I got from it is we can simplify the graph neural network by removing the nonlinear activation. So right now, the way we do things is we do the embeddings, we do all the message passing, we do a nonlinearity, and then we continue that through the rest of the graph. And so to me, it seemed like the nonlinearity probably isn't that big of a deal. That's just a simple layer that you add on. But if you look at the actual details of it, it makes it so we can't do this simplification. So the simplification that they found is basically, so this is explaining the calculation in more detail, basically in matrix form, what we're doing. So we have a big adjacency matrix saying what they're connected to. We have the degree matrix saying the number of connections, I believe, and then we can take those together. And then we have the embeddings, which is the calculated embeddings for all of the various different features. And then we can do this multiple times, basically. So we have the adjacency times the embeddings times the weights for a certain layer. So if this is layer 1, it's the first hop. Then we have embeddings of 0, the weight matrix for the layer 0. And then we do all this, and then we apply the ReLU, and then we can do that multiple times. So this gives us the embeddings for k+1, and then we roll that forward. So now we do this process again on k+1 instead of just k, and that would build us k+2.
Hey, Ryan, we lost your audio for like 10 seconds. I think your internet was slow.
Okay. Am I back? I'm back.
Yeah,
Okay.
you're good now. I think you can keep going.
Okay, perfect. So I don't know exactly what part we missed, but we can do this process where we're calculating this matrix multiplication and passing forward, and we're doing the first hop and the second hop and then all of that stuff. So we're going deeper into the graph. And one of the interesting things about forming it like this, let me see. They don't call it out specifically, but the gist of this idea is removing this ReLU nonlinearity, anything that you have there, makes it so that you can do the power iteration method. So basically, you have this A adjacency matrix, and you can say, just take that to a certain power to then iterate the depth of connections, basically. So if you want to look two hops deep, you do this A matrix to the second power, third power, fourth power, basically, and it's simulating kind of the interconnections. We'd have to look at the math in more detail to actually get into this, but you can kind of iterate this A matrix and say how deep you want to go, and then you just multiply by the E and the W, and then it makes it so it's this very simple matrix multiplication calculation where you don't have to do all of the actual kind of message passing and all of that stuff. You're just doing one big matrix multiplication and choosing the K and all of that stuff. So I think that this is a deeper topic that we would have to actually dig into the math for. But that's basically the idea, is if you remove this nonlinearity, then you can do the power iteration and you can make it extremely simple. So early on, they had a slide where they basically said you can even perform this on CPU. You don't even need GPU because you're not doing this complicated calculation every time. But the downfall of this, though, is then you don't have that rich embedding, and you don't have the nonlinearity. So you don't have nearly as deep of interactions, but you have aggregated information from all of the connected nodes, and you can go even deeper than you would before. So if a K of 10 was impossible before, now it's possible because you're just doing more iterations over that A matrix. So it makes it much, much faster, but then you're potentially losing that deep representation. So this is an option if you do have a huge graph, and you can probably do something much more quickly on this than with neighbor sampling or cluster GCN. But it won't probably get you nearly as much accuracy because it's a much simpler model. So they have shown that it does actually have good capacity because it is integrating all of the information, but you no longer have nonlinearity inside of it, so you don't have that complicated interaction. So they've found that it works well, but it's not really understood why, because you would think that it's significantly worse because it doesn't have that nonlinearity. It can't do the more complex interactions, but it does seem to work reasonably well. So consider it an option potentially. So I think that's all I am prepared to discuss today. I don't know if we have any pause for questions or anything like that.
Yeah, I'm kind of surprised that this works, Ryan.
I think part of it is you can put a lot of capacity in that initial embedding, I believe. So you embed your features, and that can already have however much interaction, and it's just that final step of doing the interactions between all of the nodes that you're skipping the nonlinearity in the message passing and that stuff. So I guess in theory you can do nonlinearity on the way in, but then not on the way out, or on the message passing section. But I'm not sure. Yeah, I think it also depends on the problem. I'd have to look at the actual papers to understand exactly how well it does.
Yeah, I think if you take out the nonlinearity, then essentially this light GCN is just like a random walk weighted average of all your neighbor embeddings.
Mm-hmm.
Because that's kind of what we saw when you sort of compute the powers of the adjacency matrix. You're doing a random walk essentially. So if you go to the 6th power, it's a random walk of length 6. So I think you're basically averaging your neighbor features up to a random walk of length 6 if you go 6 deep. So the couple slides that talked about homophily, right, is saying that if your neighbors are actually very similar to you, then you don't necessarily need all that complex expressivity. You just need to know, like, am I somebody who only has computer science friends? Well, then we're all going to have similar embeddings or whatever. But if I'm that somewhat rarer person that also has art friends, then you are going to at least get that contribution because I have those art neighbors. And so I'm going to be, half computer science, half art in my embeddings. But you're not, I don't think you can be from this, get super rich embeddings where you and I, let's say, have the exact same friends. But because your initial embedding is different from mine, in a full power GNN, you could end up having very different final results. But in this, I don't think you would. If we have the exact same friends, we're going to wind up with almost identical results.
Mm-hmm.
Not identical because we still have our original, embeddings.
Yeah.
But I think that's the, the slide said, less expressivity, right? But so as long as you and I are similar enough to begin with, then it doesn't really matter that we end embeddings based on all our friends, because we probably were similar to begin with if we had the exact same friends to begin with.
Yeah. Yeah. Yeah, I think that's an interesting point, Vance. it could be the case that you can go deeper in the graph on the light GCN. I haven't directly read the paper, so um, I can't speak to that, but that is an interesting point.
Yeah, in previous weeks, we did talk about the fact that unlike deep learning and computer vision NLP, you don't tend to go super deep with GNNs. You do get this phenomenon where, you know, if you have a certain diameter of your graph, imagine, you know, 6 degrees of separation, that kind of a thing, right? So if from 8 hops, you can get to any other node, then by the time you do an 8-layer GNN, you're getting contributions from every single node in the entire graph. They're not all weighted equally, but you are getting contributions from every node in the graph. And so then you get to this point where as you go deeper, the node embeddings starts to all kind of average out and look similar. So it is unlike other aspects of deep learning where deeper is not necessarily better. So you will see Ks of like 3 through 6. You won't necessarily see people just trying to go as deep as they can.
Mm-hmm.
I haven't done any reading on sampling. You know, ultimately, it seems to me you kind of want to calculate your encodings for every node. So at some point you have to, you know, you may be doing batches, but at some point you have to do all of them. So I don't know.
I think that that's one of the more interesting chapters because that it's very realistic that you do have a graph that you're not going to be able to fit into memory. One of the things that they discussed was in the past, people were looking and they were saying, okay, well, we always have to load the entire thing into memory, and the biggest graph we can handle is 4,000 nodes or something like that. And this makes it so you can actually operate on a graph of arbitrary size, and you don't sample it in some way that just completely breaks it. So some of the stuff isn't, I mean, it's not trivial, but the techniques that they came up with aren't like some super convoluted thing. It's just, let's do some sort of informed sampling rather than just randomly pulling points and then finding out that we can't do that. I'm sure it took several generations to figure out what works.
Yeah, by the way, the last time I looked at Neo4j was over a year ago, but their database is very fast for doing graph queries. So if you want to know, you know, which whatever type nodes are connected to these other, you know, and it's 2 hops away, blah, blah, like really, really fast for doing graph queries. But if you want to run something like Node2Vec or GraphSage, they do it all in memory. It has to fit. So you might be able to write some iterative algorithm on your own where you do a subgraph and then you store those weights and then you use those as your initial weights and you do another sub, right? But the out of the box algorithms, they just say you have to load up the features you're interested into memory, and then the algorithm runs. So you are very much limited. And I don't think it's GPU yet, but you're very much limited to what you can fit in memory.
Do you think that's
Just like we were talking
using,
about today.
do you think that's using PyTorch geometric?
No, I think they have their own proprietary implementations as of now. Maybe at some point they'll realize that they can use stuff that's like open source available. But essentially, it was interesting to see the graph database that they have that lets them do these queries is great for queries, but fundamentally it does not help them when you're running an algorithm, because like an algorithm, you're basically going to hit everything, right? So linked lists don't really do you any good. Linked lists are fast to say, what are all the neighbors of this node, and so on and so forth, right? And they're doubly linked. But if you're going to process everything, then you can't afford to do any disk access. It's going to be too slow. So you just have to load it all into memory if you're going to do any heavy processing. And that was what I've seen so far. Again, this was over a year ago, so I'm not sure, how things have evolved, but I haven't seen any announcements from them that say that they've dramatically changed their algorithms. So I think, again, for operational stuff, Neo4j is still pretty cool, but for stuff like GNNs, there's still no magic, super great solution.
Yeah.
I have one question, kind of like, yeah, like it's fairly really simple kind of thinking. Like, suppose we are having this, suppose millions, or suppose we are having 10,000 nodes of a graph, and before treating them as a graph, we just take the independent nodes and then put those nodes into unsupervised model like t-SNE. And once we get the communities formed from t-SNE, then we can actually treat those as a graph. And then we can apply the random walk like kind of stuff, like sampling stuff, and we can do our downstream tasks. I don't know how much effective it could be, but it just popped out. So yeah.
Maybe one thing I can say is that there have been some mentions in previous chapters where we said, okay, here's this cool algorithm and it can use your node embeddings. What if you don't have node embeddings? Right? So
Yeah.
you could use that technique, or you could use Levan or any of the other community algorithms, and you could even use some of the stuff we talked way back in week 2, just about using degree, using whatever, label color propagation, just all these different things. If you don't have really great data, like you don't know income and ethnicity and people's favorite hobbies, if you don't have all that data, then what you can do is you can just use these topological features from these relatively fast algorithms. And now maybe if you have 30 of them, then now you've at least got 30 features for each node, and then you can apply something like a GNN on top of that.
Yeah, it kind of really makes sense actually in that case.
Yeah, and you see that, I've seen that, Ryan, I don't know if you can remember more specific use cases, but I've seen places where in non-graph ML, people have done clustering and used that as a feature in their ML model.
Yeah, which is the feature engineering stuff.
Yeah, I think maybe security anomaly detection, like intrusion detection. You can cluster certain kinds of activity, and then you use those clusters as one of the features to augment the actual data about a given, connection, which is just, IP, port number, blah, blah, blah.
Yeah.
There's a question in chat. Do you ever consider malicious exploitation in your ML projects? I think there's many different angles to that. I've read a lot of work actually on ways that models can get stolen, essentially, ways that models can get poisoned, and ways that models can get I don't know how to describe it, intentionally broken is what I would say. and so one of, I've looked at this a lot because I think it's pretty interesting actually. You can essentially steal someone's model if you know their inputs and their outputs. So if you go to Google's API for computer vision or something like that, and you say, here's 1,000 images, here's 1,000 outputs, all of a sudden you've created a new training set for yourself, and you can basically mimic their model. So if you generally know what architecture they have, or you can at least get something in the right ballpark, you can then take that and just say, okay, I'm going to copy whatever you're doing. And then with enough iteration, with enough data through their API, you can just steal it. And then you can apply that to as much data as you want. So it's a way of getting past their security stuff. So if they want to charge you 5 cents per API call, and then you call it 10,000 times and you get an exact copy of their model, basically, then you can call it unlimited times and you don't have to be charged anymore. So that's one of the interesting kind of malicious things. But then once you have someone's model, you can probe it unlimited ways. So then you can figure out, what do I pass to this model to get it to do different outcomes? And then you can find various flaws within the within the model. So that's something that I'm pretty interested in, but I don't know a practical use for it necessarily.
Also, I was thinking, this reminded me of the Netflix competition where they were trying to improve the recommender algorithm. And then they had to stop after 2 or 3 iterations, 2 or 3 years, because of privacy concerns, because with so much data floating around, it was anonymized, but with such a large cache of data, you can actually de-anonymize some people and identify individual users. So there's several different methods, ideas, but I was just curious. Thank you.
Yeah. One of the other things that I think is pretty interesting is you can, given a model, people have figured out techniques to also extract the data that it was trained on. So you can basically plug in various inputs and you can see where the decision boundary changes, and then you trace along that, and then you can finally find something and you can say, clearly a decision boundary was made here. This is a training point that was used. And so you can basically reverse engineer the data that was put into the model, which I think is a pretty interesting technique. And also another one of those privacy concern things. We're past time now. So typically what we would do is we would transition away from the graph machine learning stuff, and we have what is sort of just open office hours. So if anyone has any projects they want to discuss, if anyone has a question about a problem, if anyone wants to continue asking questions about graph machine learning stuff, I'm sure we could do that as well. But I'm going to end the recording and then we'll kind of swap over. So if anyone was only interested in graph machine learning, feel free to hop off now, and hopefully we'll see you next week or the week after.